We have been talking about quantum mechanics from two perspectives so far. The first is photons and the quantization of the electromagnetic field. They're particles of light with smallest possible wave packets. The second thing we've talked about is how quantum mechanics influences the structure of the atom. Today we're going to put those two ideas together and talk about photon transitions for the electron in hydrogen atom. Let's go. We've been talking a lot about the information carrying capacity of space and time, that finiteness of resolution to information, if you like, and how it was parameterized, how it was coded in terms of the physical constant H, Planck's constant. And specifically, we thought about the combination HC, 1240 electron volt nanometers, that relates an energy scale to a length scale. So if we think about energy on the y-axis and length on the x-axis, it creates this curve above which classical phenomena live, things that we understand, things that require a lot of information to describe. But below this curve, we don't have enough information to understand things classically. And this is where things like the hydrogen atom, electrons, elementary particles live. We've talked also a little bit about the electromagnetic field, about photons of light, and how energy and wavelength are related in that context by specifying a discrete amount of energy required to even have light of a given wavelength, and that is given explicitly by the relationship hc over lambda. So in other words, photons really ride the curve that describes information resolution in space and time. So you might ask, well, okay, great, so we have two examples, but what exactly do photons have to do? What exactly does light have to do with the hydrogen atom? Well, light, you might recall, is electromagnetic waves. It's waves in the electromagnetic field. Light itself is composed of electric fields and magnetic fields. That was one of the great breakthroughs late in the 19th century. And then the physical parameters that we understand in terms of generating the strength of the electric field and the strength of the magnetic field, when written out in terms of those laws, Coulomb's law and Ampere's law that we understand, actually combine together to form a number, and that number, as it turns out, is the speed of light. Another way to understand this phenomena of light being electromagnetic waves, is to think about it in terms of charged particles, like electrons. Charged particles necessarily interact with the electromagnetic field, and therefore charged particles necessarily interact with light. So now that we use our quantum mechanics perspective to understand that light is also composed of finite little chunks of energy, finite little particles called photons, we know that photons should interact with charged particles like the electron. And indeed, electrons, that's the primary way that they interface with the world around them, is by exchanging, absorbing, and emitting photons, little wave packets of electromagnetic radiation. In other words, what I'm trying to say is electrons can either gain energy by absorbing that energy through a photon, or emit energy. They can lose energy by spitting out a photon with the amount of energy and wavelength corresponding to the energy that it's emitting. Now, electrons are gaining and losing energy all the time, just like basically everything else in the world around us. And indeed, a lot of the light that we see, not the sunlight, but a lot of the light that we see coming from not unnatural sources like light bulbs, for example, can be understood in terms of a kind of a collective emission of light waves coming from electrons losing energy. In fact, this is a great place to start thinking about quantum mechanics of light and the hydrogen atom. Hydrogen appears in nature as probably the simplest atom that there is, right? Just one proton and one electron orbiting around that proton. But in nature, typically when we look for hydrogen atoms, we actually find them in terms of diatomic molecules, hydrogen gas. Now, what's interesting about hydrogen gas, H2, is that at low densities anyway, you can use it to make a light bulb. The reason why you want low densities is, of course, you don't want that hydrogen gas to explode. So here's how you'd go about doing that. You could take some glass, you could evacuate a little hollow chamber inside the glass like a light bulb. You can poke some metal wires into that chamber and fill it just ever so slightly with trace amounts of hydrogen gas. pass a current through that wire, and you can watch that gas start to glow. And indeed, hydrogen gas lamps, hydrogen gas light bulbs, if you like, tend to glow with a gentle purplish color. That current injects some energy into the hydrogen gas, and that energy is enough energy, as it turns out, to break those diatomic molecules apart from one another, but it's not enough energy to rip the electron from the proton. And so the light that we're experiencing coming out of the hydrogen gas is actually associated to the cycling of the electrons inside the individual hydrogen atoms, gaining some energy from the electric current that's going into the gas lamp, and then naturally losing that energy, spitting out a photon. And that whole cycle repeats itself over and over and over again. And the aggregate result of all of that energy going in from the current into the gas and being emitted out as light is what we see, again, is that purple glow. Now, when we take normal light that we see every day, like sunlight, and pass it through a prism, we can see how that white light will turn into different colors. It spreads the spectrum out. So we see red and orange and yellow, green, blues, and purples. But something interesting happens when you take hydrogen light from a hydrogen lamp, and pass it through a prism. Instead of seeing a nice smeared spectrum, perhaps around the purple side of the spectrum, what we actually see are four distinct colors of light. 4 specific wavelengths come out, and only 4. And so instead of seeing a whole spectrum, what we actually see are distinct lines. Recalling, of course, that energy of individual wave packets of photons is related to their wavelength. What we can infer from this is that the electrons are losing energy in the form of photons, in the form of light, and only 4 distinct quanta of energy. In other words, we're learning about the internal structure, the quantum mechanical structure of the hydrogen atom simply by looking at the distinct wavelengths of light it emits, because these are the internal energy states allowed for the electron. So let's go ahead and get a little concrete here. The 4 wavelengths of light that we see are red, cyan, kind of a bluish purple, and a purple. So the red light comes out at about 656 nanometers, which corresponds to an energy of around 1.89 electron volts. So that's one energy state of the electron, or at least that's one chunk of energy that it's allowed to lose. The cyan light comes in with a slightly smaller wavelength, that is 486-ish nanometers, which corresponds to a slightly higher energy, about 2.5 electron volts. The blue-violet light, of course, comes in at 434 nanometers, which emits light at about 2.86 electron volts. And finally, that violet, that purple line, that far line on the spectrum that we see, has a wavelength of about 410 nanometers, which corresponds to just over 3 electron volts of energy. So in other words, the electrons are being energized by the electric current and are only falling in between different states, in between different energy states, configurations, if you like, that correspond to the energies presented here. Fascinating. Yet another example why the term quantum mechanics fits so well to describe this physical phenomena that we're experiencing. Now that's quite a lot of information to absorb, and in physics we like to base our understanding on simplifications for explanations for why these numbers show up the way that they do. In other words, we like to build a model that describes this phenomena that we observe. There is one quick and dirty kind of heuristic formula that can describe all of these observed wavelengths of light with just one simple equation. That equation is given by the energy is equal to some constant energy, let's call it E naught, which is 13.6, times the quantity 1/4 minus 1 over n squared. So in other words, energy is a function of this variable n, and here n is restricted to be an integer greater than 2. So 3, 4, 5, or 6. I guess in principle it can go all the way out to infinity if you really wanted to. So you can go ahead and plug n equals 3, n equals 4, n equals 5, and n equals 6 into this formula, and lo and behold, you will get precisely the energy levels that correspond to the wavelengths of light that are observed. This equation was actually found, this heuristic formula was discovered in like the 1880s by a school teacher, Johann Balmer. And in the exercises, we'll walk you through step by step how to derive this formula from the observations that we've seen. These different ends then somehow correspond to the individual states, the energy levels of the electron sitting inside the hydrogen atom, which, remember, we can't fully understand yet because hydrogen sits well below that HC curve. Generally speaking, what we understand is that integers, numbers, whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, describe the states of the electron inside the hydrogen atom, so that we can write a generic formula for all possible transitions, energy transitions, emissions and absorptions of energy from the electron in the hydrogen atom in a very similar way, right? So we can just write the general form of Balmer's series, of Balmer's formula here is just write, 13.6 electron volts times the quantity 1 over m squared minus 1 over n squared, where m and n are both whole numbers. They're both integers. And, we got to make sure that the quantity that we're studying is positive. Also in the exercises, we'll look at different values of m and explore why they don't show up in the spectra of the hydrogen atom, at least the visible spectra for the human eye. But I'll give you a hint. That's mostly because